Welcome to the IP addressing module. So far, we have covered Layer 2 and Layer 3 addressing and discussed how data is routed through a network. Now let's dive into the details of IP addressing. Earlier, you learned that every network interface has a MAC address and a Layer 3 address. You learned that an Ethernet MAC address is assigned by the manufacturer of the NIC, providing no way to logically group devices. At the same time, a Layer 3 address is a unique identifier assigned by a network administrator as a way of logically grouping devices. Each Layer 3 address has two portions, a network number and a host number. As we saw already, routers use Layer 3 addresses and routing tables to transmit data between networks. But it is not enough that the data have a Layer 3 address. Transmitting data between networks require a common Layer 3 protocol. While there are others, the most common Layer 3 protocol is the Internet Protocol, also known as IP. And IP Layer 3 addresses are known as, not surprisingly, IP addresses. The Internet Protocol uses these addresses to transmit data from a source network device to a destination network device. IP also performs other services such as fragmentation and reassembly of data or datagrams for transmission over networks with different maximum data unit sizes. We'll cover these functions in more detail later in this section. To understand how IP works, it helps to cover a little history. In the 1960s, the Advanced Research Projects Agency, or ARPA, part of the U.S. Department of Defense, started to build a wide area computer network to connect important research organizations. The goal of this network, known as ARPANET, was to share expensive or scarce computing resources. This network initially connected only 4 computers. More locations were connected over time. ARPANET was the first true network of mainframe computers and was the predecessor of the Internet. LANs, as we know them, were a concept that was years away. As time went on, other wide-area computer networks were built, but each used a different technology. It became obvious that to communicate between these networks, a new standard protocol would be needed. That new standard protocol became the Internet Protocol, which was developed in the early 1970s. IP has evolved over time. Most people today are familiar with IP addresses that look like the examples on screen. These addresses are IP version 4, or IPv4, which is used by most home and business networks. You may have also heard of the next generation protocol IP version 6, or IPv6. The major difference between the two is the size of the address. Because most people are more familiar with IPv4 addresses, we'll make them our primary focus as we introduce you to the Internet Protocol. After we show you how IP works, we'll show you why IPv6 was created and how it is different from IPv4. When a computer needs to send data, the Internet layer adds an IP header to the data to form an IP packet, also known as an IP datagram. We've been showing a simplified version of the IP header, but it actually includes many fields. Let's take a moment to look at all of the fields in the IP header. On screen, you can see all of the fields in the IP header. Notice that the source and destination IP addresses are just 2 of the fields in the header, and they actually appear near the end of the header. Click each field to learn about its function. Each device in an IP-based network must have a unique IP address. As we've mentioned before, a Layer 3 address has two parts: a network portion, commonly referred to as the network prefix, and a host portion. The network prefix is also known as the network number. In the simplified format we've been using, it's easy to see which part of the address is the network portion and which part is the host portion. Now let's replace our simplified addresses with standard IPv4 addresses. The format shown on screen is known as dotted decimal notation. Looking at these IP addresses, it isn't as easy to determine the network portion and host portion of the address. Now, at a glance, you might look at the IP addresses in Network 1 and assume that the first three numbers, 192.168.1, indicate that network's number, and looking at Network 2, the numbers 192.168.2 indicate the second network's number. In this particular example, that assumption would be correct. But as we'll soon see, IP addresses are more complex than they might appear at first. Consider the example shown on screen now. All of the IP addresses in both networks begin with 192.168.1. How does the router know which addresses are in which network? To understand how routers work, you have to understand that they don't see addresses the same way we do. In fact, the dotted decimal format we've been using was created just to make it easier for people to work with addresses. Routers use addresses in binary format, which is actually their native format. Each number in the dotted decimal format represents an 8-bit binary number. Each 1 and 0 is a single bit. So, an IP address is actually a 32-bit number that is separated into 4 groups of 8 bits each. Don't worry if you don't understand binary numbers. We'll explain them in detail in just a moment. Some of the bits in an IP address are used for the network prefix, and the remaining bits are used for the host portion. The challenge is that the number of bits used in the network prefix is not a fixed value. The network prefix might take up most of the 32 bits, or the host portion might, or they might divide the bits equally. Because an IP address does not clearly indicate which bits are network bits and which bits are host bits, every IP address has a corresponding 32-bit network mask, also known as address masks, subnet masks, and simply net masks. Network masks are used to identify the network portion of the address. Network administrators assign a network mask to each interface on each device, just like they do IP addresses and default gateways. If you launch a command prompt on your PC and type ipconfig, you'll see the mask configured for your computer. The IP address and network mask together identify which bits are used for the network prefix and which bits are used for the host portion. In a mask, if a bit is turned on, in other words, if it's a 1, the corresponding bit in the IP address is used for the network prefix. If a bit is turned off, or a 0 in the network mask, the corresponding bit in the IP address is used for the host portion. So, in the example on screen, the first 24 bits of the address are the network portion because the corresponding mask bits are turned on. Now, in this example, the first 27 bits are the network portion for the same reason. But before we start discussing the details of IP addressing and network masks, we need a math lesson on how to convert binary numbers into decimal numbers and back again. As we mentioned, IP addresses consist of 32 bits, each of which can either be a 0 or a 1. If we tried to use these bits as one big chunk, it would be very difficult to manage and understand. For simplicity and clarity, we break the 32-bit address into 4 groups of 8 bits each. Each group of 8 bits is also known as a byte, or an octet. As we mentioned, to help humans work with IP addresses, each octet is converted into a decimal number. In this section, we'll take a look at how to convert the binary number shown on screen into a decimal number in dotted decimal notation. When humans deal with numbers, we use the decimal number system, also known as the base 10 system. This system uses 10 digits, 0 through 9, that can be grouped together to form a decimal number. Each position within a decimal number represents a power of 10. The table on screen shows places for the first 4 powers of 10. 10 to the third power is 1000, or the thousandths place. 10 to the second power, or 10 squared, is the hundreds place. 10 to the first power is the tens place. And finally, 10 raised to the 0 power is the ones place. Remember that any number raised to the 0 power is always 1. Now, let's look at an example. The decimal number 3407 can easily be broken down into the different powers of 10 shown on screen. If you do the math for each position in the decimal number, you can see how we come to 3407. While the decimal system is a base 10 system, the binary number system is a base 2 system. This system uses only 2 digits, 0 and 1. In the binary number system, each position represents a power of 2, as shown on screen. In this table, we show places for the first 8 powers of 2, which is equivalent to 1 octet of an IP address. Because any number raised to the 0 power is 1, 2 raised to the 0 power is still the ones place. The next bit position is 2 raised to the first power, or the twos place. Next is 2 raised to the second power, or the fours place. This scheme continues all the way up to 2 raised to the 7th power, or the 128th place. In a binary number, each digit is 1 bit, so the table on screen could hold 8 bits. Let's look at an example. We'll start with the first octet of the 32-bit IP address and determine its decimal equivalent. On screen, you'll see each position represented with the correct power of 2. Remember that when we looked at decimal representations of numbers, a 1 in the hundreds place means one group of 100. A 1 in the tens place means one group of 10, and so on. In binary representation, a 1 in the 128th place means one group of 128. A 1 in the 64's place means one group of 64, and so on. Here you see that only the 128th place and the 64's place are turned on, because these bits are all set to a 1. All others are turned off or set to 0. By adding 128 and 64, we discover that 192 is the decimal equivalent of the binary number. Now let's determine the decimal equivalent of the second octet. Following the same procedure, we determine which bits are turned on, calculate their decimal equivalent values based on the powers of 2, and add these numbers together. Here, the 128's place, 32's place, and the 8's place are all turned on. Adding these 3 values together, the decimal equivalent of this binary number is 168.